Hello and welcome to David's math class. In this video, I will show you how to derive the roots of a cubic equation. Let's go. So, first of all, write the cubic equation in its general form. Ax cubed plus bx squared plus cx plus d is equal to 0. And then divide by a, so that we get rid of the leading coefficient of the equation. What we end up with is this, and the next thing we're gonna do is complete the cube. Here we have x cubed, there we have b over a, that's 3 times b over 3a times x squared, and then we can write down 3 times b over 3a squared, that's b squared over 9a squared x, and then b cubed over 27a cubed, add that, and now we subtract what we added. We get minus b squared over 3a squared x minus b cubed over 27a cubed, and then we add what's left, plus c over a x plus, so that's an x plus d over a, and that is equal to 0. These factors have to be x plus b over 3a cubed. Let's see, what do we have with x? We have minus b squared over 3a squared. Here we have multiply by 3a, and we get plus minus b squared plus 3ac all over 3a squared x, and here we have minus b cubed over 27a cubed plus d over a, that's by amplifying here by 27a squared, we get plus minus b cubed plus 27a squared d all over 27a cubed is equal to 0. Next, we forcefully add b over 3a times this, so that we can have an equation in respect to x plus b over 3a. So we have x plus b over 3a cubed plus minus b squared plus 3ac all over 3a squared times x plus b over 3a. Then we subtract what would be left, which would be minus b cubed plus so let's subtract that, minus b cubed plus 3abc all over 3a squared times 3a, that's 9a cubed, plus well, let's see, minus b cubed plus 27a squared d all over 27a cubed, and we can further write this as x plus b over 3a squared plus minus b squared plus 3ac all over 3a squared x plus b over 3a, and then we multiply here by 3, we get minus 3b cubed, so that's plus 3b cubed minus b cubed, that's 22b cubed, 2b cubed, and then minus 9abc, that's what we write, and then we add 27a squared d, a squared d all over 27a cubed is equal to 0. Great. So what we'll do is write this to be d, this to be p, and this to be q. If we do this, our little equation will turn into a simpler one. So t cubed plus pt plus q is equal to 0. We can now get rid of this. But there is a formula which states that u plus v cubed is equal to 3uv u plus v plus u cubed plus v cubed. By bringing this to the left, we get u plus v cubed minus 3uv u plus v minus u cubed plus v cubed. That, my folks, is equal to 0. And next, we take u plus v to be t, minus 3uv to be p, and minus u cubed plus v cubed to be q. And that's exactly our original, our simplified equation. So, let's create a little system. This doesn't matter, we'll just remember it. U plus v is equal to t. Minus 3uv is equal to p. And minus u cubed plus v cubed is equal to q. Which yields us uv is equal to minus p over 3 and u cubed plus v cubed is equal to that's q with a minus sign in front of it. And now what we can do is cube this so that we have an equation in respect only to u and v, u cubed and v cubed, we'll get u cubed v cubed is equal to minus p cubed over 27 and u cubed plus v cubed is equal to q squared. Alright, now what we can do is square this term, this equation, and then we get u cubed v cubed. Actually, we can multiply this by 4, so you'll see why in a minute. 4u cubed v cubed is equal to minus 4b cubed over 27, alright, and u cubed plus v cubed squared, that would be u to the 6th plus 2u cubed v cubed plus v to the 6th is equal to, so this would be actually minus q. This is q squared. Alright, what we do is take this to be 2, this to be 1, subtract 2 from 1, 1 from 2, and we get u to the 6th minus 2u cubed v cubed plus v to the 6th is equal to q squared plus 4p cubed over 27. Great. Now we take the square root, right here, and we get u cubed minus v cubed is equal to plus or minus square root of q squared plus 4p cubed over 27. But recall that u cubed plus v cubed was equal to minus q. So, in return, we get 2u cubed is equal to minus q plus or minus square root of q squared plus 4p cubed over 27. And then, if we divide by 2, we get u cubed is equal to minus q over 2 plus or minus square root of q squared over 4 plus p p cubed over 27. Alright, let's just leave out what's important. Alright, and now notice v cubed, so v cubed is equal to minus q minus u cubed, which is equal to minus, let's see, minus q over 2, that's minus q over 2, that's minus q plus q over 2, that's minus q over 2, and then minus plus, since we have a minus the sign changes, minus plus square root, square root of q squared over 4 plus p cubed over 27. And now, since u and v are could be chosen randomly, since our original equation was symmetrical to u plus u and v, here I'll just write it down again for you. U plus v cubed minus 3uv, u plus v, minus u cubed plus v cubed is equal to 0. Notice how changing u and v, interchanging them, would not yield us any different result. So what we can ultimately do is choose u cubed to have a plus right here and v cubed to have a minus right here. Alright, I just delete this. So, let's recap. We had uv is equal to minus p over 3 and u cubed plus v cubed is equal to minus q. And then we had u cubed is equal to minus q over 2 plus square root of q squared over 4 plus p cubed over 27, and v cubed, cube is equal to minus q over 2 minus square root of q squared over 4 plus p cubed over 27. Now, we could take the cube root and get our u and v, but we have to be careful because, first of all, whatever number you take a cube root from, there will always be 3 cube roots you could choose from. Let me show you. So, if you have your complex plane, this is 0, this is x, this is y, and of course this is the real axis and this is the imaginary axis. Say we have a point right here. I'll draw it in red for you. And this point has an argument theta and a radius r. This would be r times cosine of theta plus I sine of theta. Taking its cube root would give us it will be a pair of 3 numbers. So first, what we do is divide the argument by 3. Let me just make a little division for you guys. Alright, so this doesn't matter to us anymore. Look, you can see it's the division into 3 parts of the angle, and we take this part, make sure it has length cube root of r. Well, say it's right here, so this point has an angle of theta of theta over 3 and the module of cube root of r, absolute value, radius, whatever you want to call it. This number is cube root of r times cosine of theta over 3 plus I sine of theta over 3. But think about it. This number could not only have been written like this, it could have also been written as r times cosine of theta, wait, let me just, theta plus 2k pi, yes, plus I sine of theta plus 2k pi, where k is an integer. So when we divide this angle by 3, we could also use the other angles which have 2 pi, a multiple of 2 pi in them, to then divide by 3. So say we had r times cosine of theta plus 2 pi plus I sine of theta plus 2 pi. Our new number would be r taken its cube root times cosine of theta plus 2 pi over 3 plus I sine of theta plus 2 pi over 3. And if our number were r times cosine of theta plus 4 pi plus I sine of theta plus 4 pi, that's it, our root would have been cube root of r times cosine of theta plus 4 pi over 3 plus I sine of theta plus 4 pi over 3. So really what we do, is add 2 pi over 3, 2 pi over 3 again. If we add it one more time, we'll get 6 pi over 3, that's 2 pi, a full circle, so we end up back at this one, this cube root. So really, what this tells us is the other cube roots have the same radius, but are spaced out by an angle that is equal to a whole circle divided by 3. That's 2 pi over 3. But since the radius is the same for all the cube roots, and the angle spacing between them is a third of the complete circle, we actually end up with the vertices of an equilateral triangle. So that would be the second root, and I'll just draw this right here, the third root. So this, let me just change the marker. So you can see them right here, 1, 2, 3. These are the 3 cube roots. All right. So really, if we think about it, let's think in complex multiplication. Remember how there is a number for which omega cubed is equal to 1. And the solutions of this equation are actually called the cube roots of unity. So our 3 solutions to this are W1 is equal to 1, W2 is equal to minus 1 plus square root of 3i over 2, and our third root is minus 1 minus square root of 3i over 2. And I'll just show it quickly to you that this is really the result we'll be getting. I just draw the complex plane for you again. Alright. So what happens is, here we have 1, and this is also the cube root we were talking about. Then recall that the cube roots lie on an equilateral triangle with set vertices. Of course, its center has to be in the center of the complex plane, because the radii of the cube roots are the same. So that means they lie on a circle, really. They lie on a circle, if you want to see it in action. Let me just rewrite this. Alright. 1. And these are our second cube roots. Oh, what is this? Well, let me just draw out the equilateral triangle for you. Here's the origin, and this part, since this is a median center, I mean the center of weight of the triangle, this part is 1/3 and this one is 2/3. And since we have 1 here we have 1/2 of that, which is 1/2, but since it's negative, it's minus 1/2. And also, when you look at how this scales up, we recall that this is a 60-degree angle, so it's 60 degrees right here. And we have the sine of this is square root of 3/2 over 1. Therefore this segment is square root of 3/2, which yields us that this guy is minus 1/2 plus square root of 3/2i, and this is minus 1/2 minus square root of 3/2i, through symmetry. Great. So we have obtained our three solutions of this equation. And now, one more thing to consider. Multiplying a complex number by the cube root of unity is equivalent to sliding it, rotating it by 0 degrees, 120 degrees. Actually, let me write this in radians. 0, that's 2 pi over 3, and 4 pi over 3. So, in the end, the number with argument theta over 3 and the radius cube root of r, we shall write it as cube root of r times cosine of theta plus I sine of theta over 3 over 3. Actually has two more numbers. We can call this to be a c. This guy right here is omega times 1 times c, and this is omega is actually that's omega 2. Let me just correct that. And the third one would be omega 3. But notice that omega 3 and omega 2 are just conjugate numbers. So that would be omega 2 conjugated. So in the end, what we have is that cube root of r, if cube root of r is a principal root, that means the real argument is the greatest, and if it happens that there are 2 points which have the same real argument, maximal real argument, then we take the one with the positive imaginary part. The other 2 roots of in the complex plane, so let me just, would be omega 2 times cube root of r and omega 2 conjugated times cube root of r, and these are our 3 cube roots. So that's cube roots of r. Why did I write it like that? Sorry, that's actually c. So that's are the cube roots of c. All right. Let's move on. No, sorry about that. We're not gonna. Let's just q squared over 4 plus b cubed over 27 minus square root of q squared over 4 plus b cubed over 27 delta, which is equal to q squared over 4 plus p cubed over 27, the guy we see right here and right here, is called the discriminant of the third degree equation. Discriminant. You'll see why later in this proof. So the next thing we do is take the cube roots of these numbers just as we intended to, and we did before. So u 1, 2, 3 is equal to cube root of minus q over 2 plus square root of delta. Recall that's the discriminant. And v1, 2, 3 is equal to cube root times of minus q over 2 minus square root of delta. This is multiplied by 1 omega 1, 2, 3. And notice, since uv is a real number, minus p over 3 is a real number, because in third degree equation we choose a, b, c, d, the coefficients of the equation to be real numbers. That must mean the arguments of the complex numbers u and v are opposite. So these guys have opposite arguments. Or we can write this simply as theta of u is equal to minus theta of v. Alright. Since we have understood that, this simply means that we multiply this cube root by the conjugate, so that when these two are multiplied, they give a real number. So this is omega 1, 2, 3 conjugated. Right. In the end, notice that we consider cube root to be principal root. And now recall t is equal to u plus v. X plus b over 3a is equal to t, which yields us x plus b over 3a is equal to u plus v, which means x is minus b over 3a plus u plus v. Recall that delta is equal to q squared over 4 plus p cubed over 27, and we get x 1, 2, 3 is equal to minus b over 3a plus cube root of minus q over 2 plus square root of delta times omega 1, 2, 3. Let me just delete this right now, and then plus cube root of minus q over 2 minus square root of delta times omega 1, 2, 3 conjugated, where omega 1 is equal to 1, omega 2 is equal to minus 1 plus square root of 3 over 2, here an I, and omega 3 is equal to minus 1 minus square root of 3, or I over 2. Great. So essentially we have found our solution. Let's just rewrite everything in its complete glory. So we'll just get rid of everything here. And now we have an equation ax cubed plus bx squared plus cx plus d is equal to 0, where a B, C, D are real numbers and A is different from 0. Now, divide by A. Actually, no, that's how we solved it. Remember that we divide by A and then complete the cube, and we get two numbers. B is equal to minus B squared plus 3AC all over 3A squared. Q is equal to 2B cubed minus 9ABC plus 27A squared D all over 27A cubed. Delta is equal to Q squared over 4 plus B cubed over 27, and then the three roots of the cubic equation are minus B over 3A plus square root of minus Q over 2 plus square root of delta times omega 1, 2, 3 plus cube root, is that right? A cube root of minus Q over 2 plus square root of delta minus square root of delta times omega 1, 2, 3 conjugated, where omega 1, 2, 3 are the solutions of omega cubed is equal to 1, and the cube root is the principal root. And of course, this can also be written as omega 1 is equal to 1, omega 2 is equal to minus 1 plus square root of 3I over 2, and omega 3 is equal to minus 1 minus square root of 3I over 2. And that, folks, that is our answer. Great. Now, you notice that I called this thing the discriminant of the cubic. Why is that so? Why is it a discriminant? I will show you right now. So, let's delete this. So, recall that the roots, I'll just write it again for you, you don't have to pay very much attention. This cube root minus q over 2 plus square root of delta, and that's cube root of, wait, sorry, forgot to multiply by omega 1, 2, 3, don't forget that. Plus cube root of minus q over 2 minus square root of delta. Notice this is outside the cube root, times omega times 1, 2, 3. And of course the cube root is principal. Always remember that. And omega 1 is equal to 1, omega 2 is equal to minus 1 plus square root of 3I over 2. Omega 3 is equal to minus 1 minus 1 minus square root of 3I over 2. Let's give you an example. So, if delta is greater than 0, let's just give some values for delta, like delta is equal to 1 and minus q over 2 is equal to let's say 2. And we have here, what we have here is cube root of 2 plus 1. That's cube root of 2 plus 1 plus cube root of 2 minus 1. That's cube root of 3 plus cube root of 1, that's 1. So this is our first solution, and I just draw it for you. This is, let's say this is 1, add cube root of 3, that would be cube root of 3 plus 1. Now recall, this is really a sum of two numbers. So this would be 1 and this would be cube root of 3. And this sum is equal to cube root of 3 plus 1. But notice we can fake the cube roots, one right here, since it lies on the 3 cube roots of 3 lie on a an equilateral triangle. I'll draw this in red, and I'll draw the ones for 1 in blue. This is 1, this is 1, and this is 1. And the way you add this is look at the pairs of red and blue which have conjugate angles. Like, let me just change the color. This one and this one. So for our second solution, you add these two together, like they are vectors, and you get this to be your second complex solution. And now if we add this together, this is our, wait, let me make this in green. This is our third solution, this is a solution, and this is a solution. So we have, by the nature of these cube roots, we have one real solution and two complex solutions. So we can safely say that we have one real solution and two complex solutions. Now, if delta is equal to 0, what we end up with is this sum, which is cube root of minus q over 2 plus cube root of minus q over 2, that is equal to cube root of minus q, or rather minus cube root of q, since q is a real number. We'll just draw this on the xy plane. If we have, so here we have cube root of minus q, and this is a duplicate. We have cube root of minus q as well, of minus q over 2. Let me just change that. There we go. What we end up with is So I'll just construct that in green as well. This is cube root of q taken with a minus. Our first solution. Notice that we didn't add this minus b over 3a because it really doesn't make much of an impact. It just slides the roots of the equation to the right or to the left, so that really doesn't matter. Next, our second root. So notice we have a cube root, and there are three ways to take the cube root. They form an equilateral triangle with its origin in the center of the plane. And there is two more ways to add this. So we could add them like this. To get a root right around here. Let me just make it green. I'll just delete this, and that will be green. And next thing is that if we choose to add those roots in another way, like we take this is the second root plus the third root, that's this. But if we take the third root plus the second root and add that, really here we have an overlapping two cube roots that are together. So really what happens when we add a pair like this, so it would be something like this: blue plus red, red plus blue. We still end up with the same point lying on here, on where I've drawn right here. So what we can safely say is that when you have delta to be equal to 0, you get two real solutions and one is a duplicate. That's why there are three. Alright. You could technically say there are three real solutions. So just three real solutions and one is a duplicate. Alright. And now the real deal is right here. When delta is smaller than 0, what happens is, let's consider cube root of 1 plus 3i plus cube root of 1 minus 3i. Notice delta smaller than 0, square root of delta is an imaginary number, and then the sum looks something like this. But notice these are complex conjugate numbers, and I'll just draw this out for you. 1, 3i minus 3i. I draw them with, let's say, what color? That would be, let's say, a red. Their sum will be a real number because the imaginary parts cancel out. But because the cube, taking the cube root, does not change really the fact that these two are conjugate pairs, you will get the sum of this, like taken with the cube root. Let me just delete this. So the blue dots are the cube roots and the red dots are just the numbers in the cube roots. You get your first solution to be this. Then, when you rotate 120 degrees or 2 pi over 3 radians, you get two more solutions. Bam. You know what? I ran out of colors, really. Let's just delete the red ones since we don't care about them anymore. And this, and this. And I just made the drawing bigger. Alright? So, these three are the cube roots of 1 plus 3i, and here, complex conjugate pairs, we have the cube roots of 1 minus 3i. And notice, first pair, this plus this, gives us a real solution. Next pair, this plus this, imaginary parts cancel out, this gives us a real solution. And then this plus this cancel the imaginary parts, and then we get a real solution. And these three solutions are real. And you could almost imagine a cubic, so like this cubic graph passing through these three roots. That is it, really. When we have the discriminant delta to be smaller than 0, we get, simply put, 3 real solutions. And that's it. So, I hope this video was very informative to you. Wait, we cannot stop right here. Let me just show you how you would solve a cubic equation using the formula I gave you. So, alright, so here's on how to solve the equation x cubed plus 2x squared plus 4x plus 3 is equal to 0. Set b equal to minus b squared, that's 4, plus 3ac, that's 12, over 3a squared, that's 3, and this gives us 8 over 3. Q equal to 2b cubed, that's 16, minus 9abc, 72, plus 27a squared b, that's 81, all over 27a cubed, that's 27, that gives us 9 plus 16, 25 over 27. Delta will be equal to 25 over 27 over 4 squared plus, 25 over 27 squared over 4 plus 8 over 3 cubed over 27, and this is equal to 625 over 729 all over 4 plus 512 over 729 and this is equal to, let's see, 156 point, well 25 plus 512 over 729, which is equal to 668 over 25 over 729, which is equal to, let's see, multiply this by 4, we get 8 times 3 plus 3, 66 times 3 plus 2, 66 times 4, that's 264, 267. Let's quickly check on our calculator. 260 divided by 4. Yes, that's good. And that is over 2. Wait, let me think a bit. So 729 all times 4, that's 36, 8, 28. So that's 2916 over 2916. And then you simply take x1, 2, 3 to be equal to minus b over 3, which is minus 2 over 3, plus square root of minus 54 over 27. Oh, one more thing. Notice that this is positive, so we have only one solution, which is real. Minus 54 over 27 plus square root of 2673 over 296 times omega 1, 2, 3 plus the same thing but with a minus 6 square root of 2673 over 2916 times omega 1, 2, 3 conjugated, where omega 1 is equal to 1, omega 2 is equal to minus 1 plus square root of 3i over 2, omega 3 is equal to minus 1 minus square root of 3i over 2. And that's it.